guys, you're welcome to my channel. Today we are going to be talking about magnetism and electromagnetism. I urge you to watch this video till end. You are going to enjoy this topic, and I'm very sure when you're done with the class, you will be able to teach your dog. Yes, not only your sisters or your brothers, I'm talking about your siblings. You are not going to teach them only, not even your students, but you will be able to teach your dog. Cool. When you talk about magnetism and electromagnetism, we all know that magnet is something that has been discovered in centuries, in the ancient time. That is, I can't even keep the dates in which they discover the concept of magnetism. Unlike that of electricity that was discovered in 1700. Okay? We are not here to talk about their history, but we're going to talk about the concept of magnetism and electromagnetism. Cool. If you are yet to do that, don't forget to give us a thumb, like this video, share with your friends, and if you are yet to subscribe to this channel, don't forget to do that. Kindly subscribe and let's see how we can produce more useful content to affect your academics life positively. Thank you. Magnetism and electromagnetism. There are two different concepts that we have to consider in this class. Then we are going to start with the concept of magnetism. When you talk about magnetism, we must first of all understand the term magnet. When they talk about a magnet, you and I both know magnets, either the fridge magnet or the bar magnet or the magnets that we find in our speaker or even in our earpiece or in our phones. Now that we are familiar with magnet, what is magnet? A magnet is a substance that has a special characteristics to attract another substance, such as iron, steel, cobalt, okay, and nickel. All these are substances that can be attracted by a magnet. Are we together now? Now, any substance that can be attracted by a magnet, we refer them to as a substance that has a magnetic molecules. When a substance has a magnetic molecules in it, then that substance can be attracted by a magnet. Do we understand that now? So a magnet is a substance that has a special characteristics to attract another substance. Substance such as iron, steel, cobalt, and nickel. Are we together? Now, any substance that can be attracted by a magnet said to have what we call magnetic molecules. Now, let's keep on going. Whenever you take a magnet closer to a substance that has a magnetic molecules, the magnet is said to attract the substance. How and why? Cool. We are going to explain that as we move on in this lecture. Cool. Now, when you bring a magnet closer to an iron, it's going to attract it. When you bring it closer to a steel, it will attract it, cobalt and nickel, and so on like that. Now, I can use this magnetic effect to assess the nature of a substance. That is, you can use a magnet to identify a steel, and you can also use it to identify an iron. Now, I'm not actually going in between iron and steel, but I actually want to talk about steel and stainless steel. Now, you know, these are two different substances, although they are still steel, but steel is quite different from a stainless steel. A stainless steel will look like an iron, and by the time you take a magnet closer to it, it's not going to attract it. Why? Because a stainless steel cannot be attracted by a magnet. Why? Because its deficiency in magnetic molecules. There's no magnetic molecules in it. And what I'm telling you is this: when you see anything that looks like a metal, not all thing that looks like a metal has in it a magnetic molecules. So example of metal that doesn't have magnetic molecules in it is a stainless steel. Are we getting it now? And when you want to talk about a stainless steel, your spoon is an example. when you take a magnet closer to your spoon, if that spoon is not made of iron, then it's not going to be attracted by the magnet. But for a steel, if the material is a steel, when you take a magnet closer to it, it gets attracted to it. Do we understand that now? Cool. Now, whenever you have a magnet always have two different types of poles. That is, if this is a magnet now, here is the North Pole and here is the South Pole. Now, like you have electric charge, a positive charge and a negative charge. The same way we also have a magnet. We have a magnet that has a North and the South Pole, just like your positive and negative charge. Are we together now? So for every magnet, they always have two poles, North Pole and South Poles. Do we understand this now? How can you then determine the North Pole and the South Pole of a magnet? Let's take for instance that here is a magnet. Although this is not a magnet, but let's take for instance that this is a magnet. Now, you are not seeing it on it that probably they write on it the North Pole and the South Pole. You just have the bar magnets like this. How can you know the North and the South? What you need to do is to suspend this iron with a string. So when you suspend it with a string like this, now the North Pole of the iron is of the magnet rather is said to point towards the North axis, while the South Pole will point towards the South axis. Are we together now? But the North Pole is not always perfectly to the North Pole. You know, when you have your North Pole, South Pole, and this is what? East, and this is West. Now, geographically, this is North and this is what? South. But by the time you suspend your bar magnets that you want to determine its North Pole and its South Pole, you see it, that is, it's always like this. Instead of perfectly like this, it's always like this. Why? I'm going to explain that as we move on in this video. This is due to what? The Earth's magnetic field. I will discuss that before the end of the video. Then we understand the reason why it's not always perfectly at the geographical North Pole. Why is it always in North-South? So the one that points through the North-South is the North Pole, and the one that points through the Southwest is the South Pole of the magnet. And that is how to determine the pole of a magnet. Now that we understand that, now let's talk about different shapes of magnets. There are some magnets that you have them like this, while you have some magnets, they are like this. While you have some magnets, they are like this. Now, what is the name of this magnet? This particular magnet that looks like a rectangle like this is called a bar magnet. And this one is called horseshoe. Horseshoe magnet. And this one is called disc magnet. Are we together now? So this is a disc magnet, this is horseshoe magnet, and this is a bar magnet. How do we determine the North and the South Pole of bar magnet is what I explained just now. And for the horseshoe magnet, for you to know its North Pole, there is always dots, a white dot on the North Pole. So while the other side is going to be a South Pole. So where you see this dot is the North Pole of the horseshoe magnet, while the other side is the South Pole. And as for the disc magnet, just like you have your coin, that the coin has a head and a tail, the same thing goes to the disc magnet. The top is what? The North Pole, while the bottom is the South Pole. Do we understand this now? Now, is it possible for a magnet to have a single pole? Because all these magnets that we'll discuss now, they are having two poles, North Pole, South Pole, North Pole, South Pole, North Pole, and the South Pole. Is it now possible for a magnet to have a single pole, that is monopole magnet? Okay, thank you. It's actually impossible. For every magnet, no matter how small it is, there must be two poles, the north and the south. Even if I have a bar magnet like this and I break it into two, if I break this magnet into two like this, if I break it into two like that, what will happen is that I'm going to have here to be my north pole, while here will be south pole, then north pole. Do we understand this now? Cool. So whenever you break what? A magnet like that, you automatically have two different poles. Do we understand that now? So this is north and this is south. This is south and this is going to be what? North. Do you understand that now? So if I also break this further, I will still have what? Two poles. This to tell you that a magnet cannot have a single pole. Do we understand that now? Okay, so let's quickly look into the law of magnetism. So when you talk about the law of magnetism, just like we have the electrostatic law that states that the like charges repel each other while unlike charges attract each other, the same thing goes to magnets. The similar poles, if I have this to be north and this is south, then I have another magnet, this is south and this is north. These two magnets, they will repel each other, because they are of like pole. Are we together now? So like pole repel, like poles repel. So if I have north and I have north also, this will be south, this will be south, this would also be the same thing. They are like poles, they will also repel. While unlike poles, they will do what? Attract each other. Now, this concept of like pole that repel each other and unlike poles that attract each other is what precedes the law that will always say that induction precedes attraction. We always say that induction precedes attraction. What does this statement mean? How can you explain this statement to your dog? Cool, guys. Let's come back to class together, please. Why I always say that you can explain to your dog if you understand is that physics is just has to do with concept. Once you understand the concept of what you're talking about, you can explain it to any fucking body and they will understand it. Cool. Now, this statement, induction precedes attraction, is something that you must have been familiar with often. How do we come about this? Because we know that it is only like poles that repel, unlike poles do attract. Definitely, before a magnet, if this is a magnet, for instance, and this is a substance that I want to what? I want this magnet to attract. What will happen is, if this is the north pole of the magnet, and I want it to what? To attract this particular object. Remember, this is not what? This is not a magnet. Automatically, repulsion cannot happen. What will happen between magnet and a magnetic substance is attraction. And this attraction can only take place by this magnet inducing an opposite pole on this particular substance. I will take it again. This is a magnet, and this is the north pole of that magnet. It can also be south, whichever one. But let's say this is the north pole of the magnet. Now, this is a magnetic substance. That is, it can be attracted by a magnet. Before this magnet can attract this substance, it must induce an opposite pole on this end. So, that induced opposite pole is what is going to come before this can attract it. Am I making sense now? So, if this is north, this north pole will induce a south pole on this magnetic substance. Then they attract each other. That is why we said induction precedes attraction. If there is no induction, attraction would not take place. Do we understand this now? Okay, guys, if we actually understand this, then let's look into what we call magnetic field. What is magnetic field? When you talk about magnetic field, we are all aware of different types of fields. But in physics, we classified force into two. We classified it into contact force and force field. When you talk about the contact force, we talk about the like force and the unlike force, the frictional force. Like force is what we refer to as push, unlike force is what we refer to as pull, and frictional force is what we sometimes call viscosity. Cool, guys. Then the second type of force we have is the force field. That was also divided, it has been divided into three as well, and that is gravitational field, and the electric field, and the magnetic field. These are the three fields that we have. And what is a field? A field is a region or space where a body experiences force. So a region or space where a body experiences force is referred to as a field. Cool. In a tennis field, the tennis ball experiences what? A force. In a football field, the ball experiences what? A force. Same thing goes to gravitational field. The mass experiences what? A force. If I hold this marker now, like you can see, by the time I drop it, it falls down. It experiences the force of gravity. That is why it's being pulled down. Then electric field also, whenever we have a charge, the charge set up an electric field around it. We are going to be considering all this later. Let's focus on this. Magnetic field, whenever you drop a magnet, once you drop the magnet, just like I have this now, if I drop this magnet, this is north and this is south. This magnet already set up a magnetic field around itself. That is, any magnetic substance that moves closer to this region is going to experience the force of attraction from the magnet. Are we together now? And if that substance is far from the field, it might not experience the force of attraction. Why? Because the closer you are to the field, the stronger the magnetic force. Are we together now? The closer you are to the field, the stronger the magnetic force that you are going to experience. And the far you are from the field, the lesser or the weaker you experience the magnetic force. Are we together, guys? Thank you. I believe you understand what we call magnetic field now. Now, how can we then understand the pattern of a magnetic field? For us to understand the pattern of a magnetic field, we must understand the magnetic line of force. The magnetic line of force is what shows and describes the pattern of a magnetic field. Are we together now? Cool. It is a vector quantity because it has a direction. Now, because of the direction, that's what makes it a vector quantity, and we use it in describing the pattern of a field. Now, there are two methods in drawing the pattern of a field. Whenever you want to draw pattern of a field, we have two methods. And the first method is known as the ion filing. And the second method is the magnetic compass. Magnetic compass. Are we together now? So if you want to draw a field pattern, you either use what? The ion filing, or you make use of the magnetic compass. How do we make use of the two? I'm very sorry, at this moment I don't have any instructional material. But as a matter of fact, I will explain such that you will understand what I'm saying. Okay, guys. Now, ion filing, all you just need to do is to have a plain sheet of paper. When you get a plain sheet of paper, then place a bar magnet inside that particular paper. When you place your bar magnet there, spread around it an ion filings. When you spread around it an ion filings, then you use your hand to tap what? The paper. By the time you use your hand to tap the paper, the whole of the ion filing, they are going to what? Arrange themselves uniformly and give you the pattern of the field. I know you would like to see how the field will look like. I don't have the picture yet. I will have shown you on the screen, but I can show you on the board. Now, if I have a magnetic like this now, if this is the North Pole and this is the South Pole, this will look like this. And the same thing like this. So we have something like this now. So you have the pattern of the magnetic to look like this. Now watch something here. Okay, this is how the ion filament will do what? Will looks like. That is, this is the pattern of the bar magnet. So I have, because the line of magnetic lines always have direction. The magnetic lines has direction. Then you must indicate the direction of this field. So outside the magnet, I want you to understand something here, guys. Outside the magnet, it moves, the force moves from north pole to south pole outside the magnet. Just like we have that, it moves from positive to negative when we are talking about electric field. So outside the magnet, you have the force running towards the negative, the south pole rather, but running away from the north pole. Are we together now? So this is the field pattern for a bar magnet. Now, let me quickly use this to explain the magnetic field strength. Anywhere you see the line of force cluster like this, that is where you have them closer to each other, we have a strong magnetic field there. And when you have them far from each other, we have a weak magnetic field. And this is to tell you that at the poles, the magnetic force is always stronger compared to other regions of the magnet. So if you are using the pole to attract an object, it attracts faster and more stronger than using other parts of the body. You can see that in the diagram. Where you have the line of force closer to each other, we have a strong magnetic field there. Now we've said it that outside the poles, the force runs towards the south pole. That is, it's running away from the north pole towards the south pole. What happens inside the magnet? Inside the magnet, the reverse is the case. The force, they run from south pole to north pole inside the magnet. Inside the magnet, it is from south to north. Outside the magnet, from north to south. I believe we understand this. Cool. Now, how do we make use of magnetic compass? Well, don't mind my magnetic compass, but just take it like that. I know majority of you have seen that before. Now, a magnetic compass has the north, the south, the east, and the west, like this. Then, it has something like that of the wheel balance of a clock. So, we have the one that is red, and we have the one that is either silver at times or black, whichever one, just understand. And this is how it used to be at every instance, like this, to show you that there is a certain magnetic field, because at the center we have a magnet. At the center of this wheel there is a magnet there. That magnet is so small and it's being looped. That is, we perforate it in order for this to be able to move freely. Now when you shake your magnetic compass, at every point you always find it on a straight line. What keeps it on that straight line is the Earth's magnetic field. The Earth's magnetic field is what always makes the north and the south always in line. Note that it is because of the Earth's magnetic field, which we are going to discuss as we move on in this class. Now, let's take for instance that I have a bar magnet here now, and this is my north pole and this is my south pole, and I want to use this particular magnetic compass to draw my field pattern. By the time, permit me to use this cover as my magnetic compass. By the time you place this magnetic compass at this end, because this is a north pole, you will find the north pole of this magnetic compass facing this direction, you find the south pole facing this direction while the north pole will be facing this because of the attraction between the two. Are we together now? So you can then mark that. So when you mark that, on getting to this place also, please. On getting to this place also, you see it pointing towards the north and this is the south, so you take it. By the time you now take everything in line like that, you have something similar to what we got earlier. Are we together now? So you have something like this. Okay, you can check for video on how to make use of the magnetic compass if you are yet to get it. And if time permit me, after setting up the lab that we propose to set up, with time I'm going to have all those things there. Then we are going to have our class practically. Okay guys, so let's go on now. Now we've understand how to draw the field pattern. Now what are the properties of the magnetic lines of force? When the magnetic line of force are closer to each other, they symbolize a strong magnetic field. That is one. When they are closer to each other, they symbolize a strong magnetic field. And two, they give the shape that is the pattern of magnetic field. Three, they cannot cross each other. A magnetic field, a magnetic line of force cannot cross each other. They run from north pole to south pole outside a bar magnet, and they run from south to north inside the bar magnet. Those are characteristics or properties of line of force. Do we understand that now? Cool. Now we can now talk about the Earth's magnetic field. Now when you talk about the Earth's magnetic field, remember those things that I said we are going to use the Earth magnetic field to explain, or those things that we have as a result of the Earth magnetic field. Example is when you want to determine the north and the south pole of your bar magnet. When you suspend it horizontally like this, you automatically seeing it swinging towards the north-south. Why not perfectly at the north pole? We are going to understand that now. And secondly, the magnetic compass. Why are they always on a straight line? It's as a result of the Earth's magnetic field. Now, let's quickly look into that. Let's take for instance that this is the Earth. Okay? Now, if this is the Earth, don't mind my drawing, but let's take it like that. Let's say this is the Earth now. The Earth's magnetic field is quite similar to the magnetic pattern of a bar magnet. And why is it like that? It is like that because we have the Earth magnetic field to have an imaginary bar magnet on it. Are we together now? Here is an imaginary bar magnet. So if I have here to be my north pole and I have here to be my south pole, are we together now? So we have the field pattern to be something like this. That is the field pattern for Earth's magnetic field to look like this. Okay? Don't mind my drawing. But all we have to look into is to understand the concept correctly. Are we together, guys? Now look at something. If you look at my diagram, I'm here to show you the direction of the line of force. Yes, because I want to explain something to you. If you look at this now, we said the Earth's magnetic field is approximately an imaginary bar magnet. Take it again. Earth's magnetic field is like an imaginary bar magnet. So if this is an imaginary bar magnet and this is my north pole and this is my south pole, now I want you to understand something something between the Earth's magnetic pole and the geographical magnetic pole. if I have this to be my geographical pole, this is north and this is south. It's always on a straight line. But that of the Earth's magnetic field is about 15 degrees away from the geographical pole. You can see it like this, and that's why you see this magnet acting like this. Now, this is South Pole and this is North Pole. You know, if you suspend a bar magnet on the surface of the Earth, you always see it pointing towards the north-south. This is because the Earth's magnetic pole that attracts this body to come up is not in the same is not in the same axis as the geographical pole. Are we together, guys? Cool. If that should be the case, this is the South Pole, right? Normally. But because what? Because the North Pole will attract the South Pole. Are we together now? And the South Pole will attract the North Pole. Automatically, for this particular body to point upward, then it shows that the Earth's magnetic field is South Pole, is here. Are we together now? That's why you see this one attracted in north-south direction. So it's about 15 degree north-south direction. So you have to note that those are objective questions. So this is the South Pole. Why? The North Pole of this Earth's magnetic field attracts the South Pole of the bar magnet. So this place becomes our North Pole. Then I can now give my line of force now to look like this. Okay? So we have it like this. So this will go like this, and this will be like this, So, and this is like this. Do we understand this now? Cool. This is that about the Earth's magnetic field. Do you understand this now? So you can easily sketch this out, and you now understand the reason why when you want to determine your north and the south, the reason why this thing is not always pointing towards the north, why it used to point towards north-south. Are we together now? Because the magnetic pole, the Earth's magnetic pole, is 15 degrees away from the north-south geographical pole. Do you understand that now? Thank you, guys. So let's move on now to the strength of the Earth's magnetic field. The Earth's magnetic field is quite small when it comes to strength. Now, remember that the strength of a magnetic field is measured in Tesla. That is, the unit is Tesla, and that is capital letter T. As for the Earth's magnetic field is about 50 microtesla. The value for the Earth's magnetic field strength is 50 microtesla. While our bar magnet is about 0.01 Tesla. If you look at this now, you will see that the bar magnet is stronger in strength than the Earth's magnetic field. Why is it like that? If you look at this now, you will see that the bar magnetic field strength is 200 times stronger than the Earth's magnetic field. Now, let me tell you what will happen if the Earth's magnetic field strength should increase. If the Earth's magnetic field strength should increase, every magnetic substance that we have on the surface of the Earth will come together and magnet each other. And you know what might actually happen to you, because you might find yourself in between them. Okay, guys, that's just it. So we have that the bar magnet is 200 times stronger than the Earth's magnetic field. Now, how do we get our Earth's magnetic field? Is it that there is a certain magnet somewhere that actually serves as our Earth's magnetic field, or how? Absolutely no. We don't have any magnets anywhere. But the Earth's magnetic field is as a result of effect of electric current. I'm going to make a video on that, on how to explain how we come about that. Are we together now? as a result of some molten substance that move around the core of the earth. Are we together now? So, mind you, whenever we have a current, automatically around that current there is a magnetic field. I'll be explaining that. I'll be explaining how it come about that in my next video by His grace. Yes, by His grace. Okay, but in a nutshell, we don't have a magnet in anywhere. We have the magnetic field of the earth as a result of the effect of electric current, what we call electromagnetism. Is as a result of electromagnetism. That is how we come about the Earth's magnetic field. And that's why if I tell you that without electricity the universe will not exist, I believe now you should not doubt it. Even without electricity you cannot think. Without electricity you cannot move from one place to another. That is a talk for another day. Let's continue from where we stop, and we shall consider the concept of electromagnetism now. Now, when you talk about electromagnetism, we need to understand, we already understand the concept of magnets now, right? So we need to understand the concept of electricity before we can now combine the two together. Because by the time you look at the statement electromagnetism, we are looking into the relationship between magnet and electric. Remember I told you at the beginning of this video that magnetic effects, that is magnet, is what we have discovered in ancient time. But electricity was discovered in 1700th century. Now, let us look at what we call electricity. When you say electric current simply means the movement of electron. The rapid movement of electron is all referred to as electric current. In a nutshell, are we together now? Now that we understand electric current, the movement of that electron has different effects. We have the heating effect, of current. We have the chemical effects of current, and we have the magnetic effects of current. Let me quickly explain all these effects. That is, whenever you have electric current can cause any of these three. That is, when current is passed through a conductor, it is converted to heat according to Joule's law, where we have IVT, current, voltage, and time. This is equivalent to quantity of heat. And this is the same thing that happens in our bulb. By the time you switch off the bulb, current is not running in the electric conductor. By the time you switch on the bulb, current that runs in the electric conductor changes to heat of the filament, and that brings about the lightning effect. The heating of the filament is what results to the light that you see that the bulb is producing. I'm not going to talk much about this, but I believe you understand that now. And as for the chemical effects, when you talk about the chemical effect of current, that is what we call electrolysis. And what is electrolysis? Electrolysis is the dissociation. When a compound dissociates, that is, a compound break into its simplest form. Are we together now? The breakage of a compound into its simplest form as a result of current that passed through it is what we call electrolysis. When a compound breaks into its simplest form as a result of currents that pass through it is what we refer to as electrolysis. Example is the electrolysis of water. the electrolysis of water. Now, if I have water, H2O, and electric current, I, let me use I to represent my electric current, pass through this water, is going to break it into its simplest form, which is 2H2 plus O2. You can see now that this has been break into this now. We are not looking into electrolysis now. We will have continued our explanation about this decomposition. Are we together now? So this is what we call the chemical effect of current, because it is the current that pass through this material that results to this splitting up of those elements in that compound. So the main focus we want to look into now is the magnetic effect of current. So let's look into that now. Magnetic effect of current. Magnetic effect of current. Now, when you talk about the magnetic effect of current, like I said earlier, I said magnet has been discovered in centuries before we now come about current. We discover electric current in 1700. Now, a scientist, but as when they discover current, they treat current and magnets separately. That is, electric field and magnetic field are not treated together. We treat them separately until a scientist called Oster in 1820 now discovered that by the time you place a magnetic compass around the, let me say nonsense. So let's come back to class. If I have a conductor like this now, if this is a conductor, Oster, this is the name of the scientist, if I'm not pronouncing it well, Oster, okay, in 1820. He was the one that discovered the electric effect, that is the magnetic effect of current. Let me calm down. Guys, let's calm down, because at this point we need to understand a lot of things here. Okay guys, I believe you are with me now. Now let's go on. It's not easy though. Can see I'm shouting like a Christmas goat. It's for your success and for my good also. Okay, now let's go on guys. Einstein in 1820 discovered that if you place a magnetic compass around a conductor that is carrying current, by the time you switch off the electric current in this conductor, you will have the magnetic compass to be on its initial position, that is north, and this is south. But immediately you switch on the light, that current start flowing in this wire, you find out that the magnetic compass, that is the magnetic compass, will do what? Will change its position. That is, it's going to deflect. This is north, this is south. Are we together now? When there is no current in this conductor, this is what you have. Please hold on. Let me check my camera, please. Sorry guys, the camera used to stop itself. That was why it needs to take caution at times. Okay guys, let's continue please. When you have a conductor that current is not flowing in it, Einstein discovered that the position of this magnetic compass would not change. But immediately current starts flowing in this particular conductor, it shows that this change without bringing any magnets. And the only thing that can make this thing to change its position is if there is a magnet that is closer to it. Then it concludes that automatically there is an effect of magnetic field whenever current flows in a conductor. In a nutshell, a current carrying conductor produce a magnetic field around itself. Are we together, guys? I'll take it again. In a nutshell, a current carrying conductor, that is a conductor that carries current, are we together? Always produce a magnetic field around itself. Now, why are we not noticing it whenever we plug our charger and our phone? Then we bring a magnetic substance closer to that wire. What happened is because the magnetic field is not strong enough. As the magnetic field is not strong enough, the wire is not going to magnet the magnetic substance around it. How can we increase what? This electric field strength is to increase the number of currents that is flowing through that conductor. Do we understand that now? Thank you. Now that we understand that now, we can now what? Talk about different shapes. Okay, let me put it like this. We have different conductors that carry current. Are we together now? And they produce different magnetic field patterns. Now we need to understand the shapes and the kind of magnetic field that they produce. Are we together now? Now we have, for this video, I'll be considering 3 shapes and I'll be talking about their magnetic field pattern. 1, I'll talk about a straight wire. A straight wire carrying current. And 2, I'll talk about a circular loop. A circular loop. And 3, we'll talk about solenoid. Are we there, guys? I'm getting tired already, but I just have to finish this section. Okay? Now let's quickly look into that. When you talk about a straight wire carrying current, like this, if the current in this wire is moving in an upward direction, you are going to have the magnetic field around it in a circular form like this. Sorry. Are we together now? So the pattern of magnetic field around a straight wire is like this. And how will I get the direction of the magnetic field? Now, I'm going to get the direction of this magnetic field by using the Maxwell right-hand thumb rule. Maxwell right-hand thumb rule states that if you hold a conductor like this with your right hand while your thumb is pointing in the direction of the current, remember the current is moving upward, so you can see my right thumb moving upward also like this. Then the hand, the other fingers that you use to wrap that particular conductor shows you the direction of the field. Therefore, if this is my hand, you can see it shows that the direction of the field is in this direction now. Cool. Do we understand that? Thank you, guys. So you can see the way I get the direction of the magnetic field now. These are the magnetic field pattern if the current is moving upward. What happens if the current is moving downward? You can see that when the current is moving upward, the direction of the field is counterclockwise. Now, if the current is now moving downward like this, that is, I have the current pointing downward, how will I get the direction of the field pattern? You still need to apply the same rule, but this time you point your thumb downward just because the direction of the current is downward. Then you will see that my hand is going like this, so I have the field pattern to move in the direction that is clockwise. Do we understand that now? Now, how can we increase the strength of this field? you can increase the strength of the field by increasing the amount of current flowing in this conductor. Do we understand that now? So for a straight wire carrying current, you can increase the strength of the magnetic field by increasing the current flowing through the wire. So the next one that we are going to look into now is the circular loop. If I have a circular disc or loop that is carrying current like this, are we together? So the current moves in this direction. What will be the magnetic field pattern of this particular conductor? All we just need to do is to assume that this circular loop is like a straight line. Are we together? Now, if I assume that this is like a straight line, you will see that this particular arrow is pointing in downward direction. And is going to create a circular loop just like the straight wire that we have initially. The same thing is what we are going to have here. Are we together, guys? Okay, if that should be the case, what would then happen is that as this particular circle increases in size, they start becoming a straight line as they are approaching the center like this. As the loop is increasing, are we getting what I'm saying here? If you have a circular conductor, it is also like a straight wire. Then you have your magnetic field patterns to look in this manner. As the loop increases, you find that your magnetic field pattern is approaching a straight line. Are we together now? So if you look at it, this one is not as curved as this. By the time the next line coming after this one also, and they all converge at the center. Because of that, the strength of the magnetic field created in a circular conductor, the strength of the magnetic field created in a circular conductor is quite stronger than that of a straight wire. Why? So that is the reason why for a current, for a circular wire that is carrying a current, are you getting it now? A circular wire carrying a current, the magnetic field produced is always stronger than that of the straight wire. Now, how can we get the field pattern for this now? Remember that I told you when you are looking into the straight wire, you use the right-hand thumb rule. We also use the same thing here to get the direction of all this field. Now, we assume that this wire is a straight wire now. Instead of a curve, we said it is a straight wire. Now, we are going to see that this current is pointing in a downward direction here. So, as it points towards the downward direction, the magnetic field is going to move in a clockwise manner. Are we together now? You can see that the magnetic field is moving in a clockwise manner. Are you getting this now? So this is the wire here. Then this is the direction of the current. If you assume that this is a straight wire, you see that this direction of current is pointing downward. Using the thumb rule, you see that the direction of the field is going to be clockwise. But by the time you get to this place, you see that the current is now flowing upward. Then the direction of this field is going to be counterclockwise. Are we together now? So it will be counterclockwise, like this. Remember that as this loop gets increased, they are approaching a straight line at the center. So we have this now. Another question now that you need to understand about this is, where is the north pole and the south pole of this conductor? How can we get the north pole and the south pole of the conductor? We can then use the clock face rule. Clock face rule. What does the clock face rule state? The clock face rule states that if you are looking into the conductor like this, like you are looking at it like this, and the current is moving clockwise, then that place you are facing is the south pole of that conductor. Are you getting it now? That is, clockwise is south. But if I go behind, if I look at this thing behind, when I'm looking at it at the front like this, it's moving clockwise. But if I look at it from behind, it will be showing that it's moving anti-clockwise. So according to the clock face rule, it says when the direction of the current is anti-clockwise, then the face you are facing, are you getting it now, is going to be the north pole. In a nutshell, the clockwise direction of the current symbolizes the south pole of the magnet, and the anti-clockwise direction of the current shows the north pole of the magnet. Do you understand that now? Okay, the last one now, which is the solenoid. Before I go into that, how can we increase the strength of the magnetic field in a circular loop carrying current? We can increase the strength of the magnetic field simply by increasing the electric field strength. That is one. If you increase the number of currents that flow in this loop, the magnetic field strength is going to increase. Secondly, if you increase the number of loop that is carrying current, are you getting this now? The rate at which you increase the number of loop is the same rate at which the magnetic field strength will increase. If I double the loop, that is, instead of one loop, if I have two, the magnetic field strength is also going to be multiplied by 2. If I have 3, it will be multiplied by 3. Therefore, if I have n number of loop, the magnetic field strength will be n times stronger. Am I making sense? Cool. Then lastly now, for the solenoid. Okay. The solenoid, we all know that a wounded wire is what we call a solenoid, just for simplicity's sake. Yeah. How do we know if a current passes through the solenoid? Since we know that a copper wire can conduct electricity, we have this, 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 and these are the direction of the current. Are we together now? So what will be the magnetic field pattern here? The magnetic field pattern of a solenoid is like that of the bar magnet. The magnetic field pattern of a solenoid is like that of it's like that of the bar magnet. Are we together? So we have it to also be like this. This is how the electric field of magnetic field of a solenoid lies. Now, how will I fix my line, the direction line? It means for me to fix the direction of this line, I need to know the north pole and the south pole. That is the end of this solenoid that correspond to north and south. How can I discover that? I will use the clock face rule. Using the clock face rule, by the time you are looking at this solenoid like this, you will see that this is moving in a clockwise manner. Therefore, this place is the south pole. And if you look at it from here, it's moving anti-clockwise. Therefore, this is the north pole. Are we together now? So inside the solenoid, just like you have it that in a bar magnet, outside it, they are moving towards the south pole. Outside it, they are moving towards the south pole. Are we together? Outside it, they are moving towards the south pole. They are moving towards the south pole. While inside it, they are moving from the south pole to the north pole inside the solenoid. I believe you guys understand this. I'm tired, guys. You understand this? Yes, I believe you understand it now. So this is how to get the electric field pattern of magnetic field pattern of a solenoid that is carrying current. Now, last question before we go. How how can we increase the strength of this field? To increase the strength of this field, we can increase the numbers of turns in the solenoid. That is one. Two, we can increase the number of current that is passing through the solenoid. That is two. And three, we can place an iron core. Since we know that it's a soft iron core magnets very fast. If you place it inside here, the strength of the field is said to increase. I think I mentioned 3 ways in which you can increase the strength of the field produced by a solenoid. Did I do that? If that should be the case, let's stop the class here. In our next class, we shall look at the concept of permanent magnet and temporary magnet and their application. Now, the question is, if current can produce electric field, can magnetics, what am I even saying? Nonsense. If current can produce magnetic field, can magnetic field produce electric field? Yes or no? Let me know in the comment section below, and that will be our next line of discussion. Thank you for watching. Don't forget to subscribe and give us a thumb. Have a nice day, guys.